Welcome to College Bio. These are notes on Punnett Squares and some of the exceptions to Mendel's laws with Punnett Squares. You already watched the video from Professor Neighbors about inheritance patterns. So we're going to go through how to do a Punnett Square very quickly, and then we're going to look at sex-linked characteristics as our first exception, and we'll look at more exceptions next time. But I wanted to show you both of these types of Punnett squares so you know how to work them. So I'm going to share my screen with you. So with a Punnett square, you saw these on the notes videos from Dr. Neighbors. You have traits from mom and traits from dad. So if dad gives you, for example, 2 capital A's because he is homozygous dominant and tall. Okay? So that's from dad. Then you have mom, who is heterozygous for tall. And I'm going to do these in different colors so that it's a little bit easier to tell the difference between which alleles come from which parents. Let's actually, how is the blue? Can you tell? Yeah, the blue is different. Let's do blue for dad. Let's make dad blue so it's a little bit easier to see. Homozygous dominant. Okay, so what you're going to do, hopefully you've done these Punnett squares in general biology, so this is review. But all you're going to do is you're going to take dad and put him at the top here, 1 allele per column. And then you're going to take mom, and she's going to go over here to the side, 1 allele per row. And then all you have to do is fill in your boxes. So you're going to take dad's alleles down. So his capital A gets carried down to both boxes in both columns. And then you take mom's alleles across. You can switch these. It doesn't matter which one you put in which place. You just have to know that you have 1 on top, 1 on the side. The top ones carry down, the side ones carry across. So then this little A goes here and here. A couple of things to note with Punnett squares. Capital letter always goes first. Okay, that's a geneticist OCD thing. We always write the capital letter first. When we start getting into multiple alleles, you'll see a little bit of different notations. But when we're looking at a monohybrid cross, you always put your capital letter first. And that's all there is to it. So you're looking at this, you now have 2 offspring. So offspring 2 have 2 capital A's. So they are homozygous dominant. 2 are 1 of each. So they are heterozygous. 4 are going to appear tall. So that's how you interpret the Punnett square. Both of these, homozygous dominant. Both of these, are heterozygous. They all have a capital A because capitals represent dominance. They're all going to appear tall. So how you would write this then is your genotypic ratio is 2 to 2. You have to reduce it, so it is actually 1 to 1. Your phenotypic ratio is 4 to 0. For phenotype, we're actually going to write tall with it, 4 to 0 tall, because they are all appearing tall. So phenotype is what you're able to observe. Genotype is what's actually there at the cellular level. It's your letter combination. Let's try another one down here. Let's go with one parent being capital A's and one parent being lowercase a's. And to throw you off a little bit, I'm going to put my lowercase a's on top, my capital A's on the side, just to prove they don't have to go in either location. You can put them either way. I'm going to go down first. So I have little a's. Now, why am I putting them over here on the right-hand side of the boxes? This right here. Capital letter always goes first. So even if I carry the small letter first, the capital A is always going to go in front of it. So when I interpret this one, 4 are heterozygous, 4 are tall. So our ratios then are geno 4 to nothing. On the genotype, I will generally write underneath what the genotype is. So 4 are heterozygous, nothing of anything else. Phenotype, 4 to 0 tall. When you start getting differences is when you start having things like this happen. So if mom and dad are both heterozygous, you put them on your square, top and side, carry them over. So now we have our genotype. We have 1 homozygous dominant, 2 heterozygous, and we have 1 homozygous recessive. So that is our genotype ratio. Our phenotype, you have to count up the number of offspring that are going to be tall versus short. So how many of those are going to be tall? If there's a single capital A, it's going to be tall. So there are 1, 2, 3 boxes that have a capital A. So 3 tall. This is the only box that has 2 small a's, so that's 1 short. That is all there is to it with basic Punnett squares. So you're going to have practice with basics, getting those done, and then you're going to have practice with sex-linked. What happens with sex-linked is they're on the X and the Y chromosomes. So when we're dealing with sex-linked, we're going to look at characteristics that are on the X chromosome only for right now. And when you do this, you have to show that it's on the X chromosome. So if the trait is for color blindness, so A equals normal, little a equals colorblind. Okay. So this is going to be our key. So capital A is normal, lowercase a is colorblind. This is a sex-linked characteristic. We don't write just capital or lowercase a. Not how it works. In order to show that it's on the X chromosome, you have to actually have the X as your base here. And then as basically what's going to look like an exponent is where you'll put your allele. So that is a heterozygous female. If you have this, that is a homozygous male. It's homozygous because there's only one version of the allele there. Males cannot be heterozygous because they don't have a second X chromosome. So this is a heterozygous female. Homozygous male. This is also a homozygous male. This one is homozygous dominant. This one is homozygous recessive. Because there's only one copy of the allele there, lowercase a. This is a homozygous female, as is this. Two capital A's here, that's a homozygous dominant. Two lowercase a's here, homozygous recessive. Let's group these to make this a little bit easier to see. Those are both homozygous females. Okay. So how do you do this in a Punnett square? Dad always has to have a Y chromosome. If not, he's a girl. So dad is normal. So we're going to give him an X with a capital A because he has to have a capital A in order to be normal. His other allele or his other donation has to be a Y because he's a boy. So dad will be X capital A and Y. Mom is a girl, so she has to donate 2 X chromosomes. Mom is heterozygous for the colorblind trait, so she gets a capital A on one and a lowercase a on the other. Then when we put mom here, she goes in like that. Notice that we carry the base chromosome designation along with our alleles, okay? And we're going to carry that through when we do our completion of our Punnett square. The Y is going to go to the right here because we're going to write these in alphabetical order. So if they're the same letter, capital before lowercase. If they're different letters, they go in alphabetical order. So then we're going to carry mom across. So now what we end up with, we have 4 different offspring here. So you have to pay attention to what the question's asking. If it says how many offspring are colorblind, well, that's going to be 1. Because this is the only one. There's nothing else to counteract this lowercase a. And it says how many offspring are colorblind males, that's still going to be 1. If it says how many offspring are normal, That's 3 because you have 1, 2, 3 offspring that have a capital A. If it says how many offspring are normal males, it's only 1 because these 2 are both females. So depending on what it asks, you can interpret this different ways. Normal offspring is 3. Normal males is only 1. Normal females would be 2 because both of these are going to be normal because they both have a capital A. Homozygous offspring. How many offspring do we have that are homozygous? There's only 1 allele present in their genetic code. It's going to be 3, right? 1 here, and both males because they don't have the second X. Homozygous females equals 1 because this one is heterozygous. Okay, so pay attention to what the question's asking you on these sex-linked traits because you can get the wrong answer just by misreading the question. Okay, let's try another one. Let's say dad is colorblind and mom is normal. And let's give mom had a genetic test, so we know that she is homozygous dominant. Okay? So let's put mom on here and dad. Remember that you carry your base chromosome on here as well. So let's fill dad in all the way down. Let's fill mom in across. And then how many offspring are colorblind? None of them, right? Because all 4 of these have at least 1 capital A. So they are all going to be normal. So one thing this will show you is that recessive traits that are sex-linked mom decides if offspring get it. The dad can only give 1 chromosome to either sex that's going to cause this. Boys, he has to give the Y. He has no control over it whatsoever. Girls, he has to give the A that or the X that he has, no control over it. So he gives what he gives no matter what. Mom is the one that has 2 X's that she can give. So what she gives to the child is going to determine if that child is colorblind or not, or if that child has the sex-linked recessive trait or not. If she only has the recessive trait, everybody gets it, everybody's afflicted, unless dad has a capital there. Okay, if mom only has capitals, nobody is afflicted regardless of what dad has. So mom is really the deciding factor. So you're going to have practice with both of these today, sex-linked characteristics and regular Punnett squares. Go ahead and take the rest of the time in class today to work on this assignment. Also work on it at home. Get it turned in by the due date. Make sure that you ask questions if you need to. Good luck. Hopefully you enjoy this. This is one of the more fun aspects of the class for me. So go ahead and get started.